So today we'll be looking into two different types of programs. Okay, so basically we have saturation type of programs and floating type of programs. So I think we all would have studied floating point numbers, right? So if you can imagine, yeah, 8086. So this is dealing with the general numbers, and 8087 is called an arithmetic coprocessor. Right, so what is this coprocessor? It helps in dealing with floating point numbers. So one deals with the real numbers, right, uh, with the non-floating point numbers, and the other one, which is 8087, deals with floating point numbers. So together they operate, and they are able to perform much better. You can take the example of these days you have processors and GPUs, right? CPUs and GPUs. So CPUs are helping in performing the logical and arithmetic operations, and GPUs are exclusively dedicated to perform the graphic intense operations, right? So which is not a priority in CPU. Okay, but then if your system really needs that kind of horsepower, okay, that kind of graphical processing, then you will have a dedicated hardware. So similarly here, we have different types of instructions which we'll be looking into. So basically two types of family of programs we'll be looking into. One is the saturation type, and the other one is floating point. And in saturation, again, we have two types of programs. One is signed and then unsigned. Okay, so we will get started and we will understand what these are actually. Right. Okay, so first thing that you have to understand is, let us take this waveform for example. So it is reaching to its maximum value, and this becomes its positive max, I can say, plus V and minus V. And suppose I need to have a limit, okay, which means let us take a transistor for example. So here we have something called threshold, right? So threshold is something where it is not the maximum voltage, but then it's part of the voltage, which means let's take silicon for example. So silicon deals with 0.7 volts, right? And germanium deals with 0.3 volts for the threshold voltages. So similarly here, just like how we've seen in transistors, once it reaches that point, then it starts to turn on, right? The operation starts, the channel forms. Similarly here, we have set some limits for the positive side and the negative side of the numbers. So you can see this in green, right? It is marked, and this is nothing but the limits that we have at the positive side and limits that we have at the negative side. So we can limit the certain range, okay, and we can prefer the saturation instruction. So if we have to have some limits, okay, in the positive side and in the negative side, we have to use the saturation instruction. So what is a saturation instruction? Basically, I think all of you are aware of N, C, right, V, and Z. So these are nothing but our PSR, program status registers. Okay, these are all our flags. We have another flag called Q flag. Okay, so this saturation programs that we are looking into is all dealing with Q flag. So Q is nothing but saturation. Sometimes it's also referred to as overflow. So saturation instructions are dealing with Q flag, okay, moving data from the registers to the flags, from the flags to the registers, right? Okay. Now, as I was mentioning about these limits, the positive limit and the negative limits, right? So they should have some quantities, right? So we will see what are those quantities here. So when I have something from 0 to 2 raised to 32 minus 1, so that is my unsigned limit. Okay, so my unsigned limit starts from 0 and it ends with 2 raised to 232 minus 1. Okay, you can do a quick math with your calculators and find out the value for this. Also for signed numbers, right, we have the values ranging from minus 2 raised to 31 to 2 raised to 31 minus 1. Okay, so these are the limits, okay, the negative side and the positive side. Remember, as I told you, so once this happens, okay, you can see that yeah, you can see that this waveform is actually shifted, okay, in this format. So which means I am actually not getting the upper form. Okay, this was supposed to be here, right, like this, and this was supposed to be here. Okay, but I'm not getting that, but instead that part is chipped off. Okay, so that's the use of having these limits or saturation. Okay, I am saturating my waveforms, I am saturating my results, okay, to a certain value. So that's the use of these saturation instructions. Okay, right, so now that we know the limits, right, we know that unsigned value has this limit and the signed numbers have this limit. So let us get started and we will see, okay, what else it is telling us about. So when I have an unsigned, okay, as I told you, right, 0 to 2 raised to 32 minus 1, okay, so this is the unsigned. N of course is 32, right, 32 bit, and that limit is actually f80000. So how is this represented? Each f is taken here. I think all of you are aware of that. Let me just recall those concepts to you all, right? This f is taken here, right? 2, 3, 4, 8, and subsequently these zeros are here, right? So by now we all know how these are represented. And for a signed number, okay, for a signed number, as I told, it is minus 2 raised to n minus 1 to n 2 raised to n minus 1 minus 1. So let us take, for example, 16, right? And if we try to substitute it, okay, so it becomes minus 2 raised to 16 minus 1, which is 15, to 2 raised to 15 minus 1, right? Okay, so if we take the values for this, okay, so this is going to be in decimal format, right? And if I have to convert them to hex, right, so this is going to be 0007FFF. So this is in hex format, and this one is going to be FFF8000. So that number is what I have taken here. Okay, so we will be seeing these numbers also in our programs. Okay, and similarly, if I take for unsigned, as you all know, 0 to 2 raised to n minus 1, so 0 to 2 raised to 16 minus 1, so 0 to this is nothing but 65k. Okay, 65k. So which means, if I convert that, so it becomes 7FFFFF, right? If I convert this decimal to hex, can someone confirm me if these values are proper? Open your calculators and just check if these values are being converted properly to the respective forms. So first you can take the decimal format, right? You can take 65535, okay, and then you try to do a conversion. Right, so you are going to get all FFFFF, right? So we will look into that also. Now there are some values that we need to remember, or some kind of formats that we need to remember. Okay, just a moment. Yeah, okay, so we will see what those are. So let's say, for example, the instruction is going to be in this format, okay, which is SSS, SS, which is S saturation, right? RD, N, operand 2. So what is this going to do? It is nothing but, okay, it is going to check the limit. Okay, is it between minus 2 raised to n minus 1 to 2 raised to n minus 1 minus 1. So S is referring to signed, okay, signed saturation. This is unsigned saturation. U is unsigned, S is signed. So the limits are going to be checked, as I mentioned previously, right? The minimum is 0 and 2 raised to n minus 1, right? So those limits are going to be checked, and accordingly, the transfer is going to happen. So what is this OP2? This OP2 is nothing but RM or RM. Okay, so this is these are your registers. Okay, the core registers that you see in your bank, the register bank. Similarly, now we can see unsigned saturation. So I'm going to use USAT for that. Okay, and now the limits are going to change, as I mentioned, right? So signed and unsigned have the different limits. So it's going to check if it's going to be in this range or not. Okay, and if it's not in that range, then default values will be set. Okay, so those default values, as I told you, right, which is 7FFFF and 38000. So those values are going to be set, right? Just the values that you saw here previously. Yeah, these values. Okay, so we will see that in the program also when I do the execution. Okay, so the Q flag is set when saturation occurs and no other flags are affected. So this is one of the speciality of saturation, right? The Q flags are only affected. So you cannot find the other flags like negative, okay, carry, overflow. So all those flags are not affected, but then only the Q flag is affected. Okay. Given a value, these instructions limited to the range of n bit representation. So whatever value that I have, so that is going to limit it. So it's just like checking if the value is falling between this range, okay, which is nothing but if it's saturated, then minus 2 raised to n minus 1 to 2 raised to n minus 1 minus 1, right? So is it falling in this range or is it falling in this range? So the instruction that you are going to give plays a very important role. Is it in signed format or is it in unsigned format, right? So that should be taken care of. So let's see a flow chart here, right? So you'll be able to understand. So I just give a number, okay, and then it's going to check, is it minimum, right? So if it's minimum, right, so these are the conditions that are going to be checked. Is it 0 to 2 raised to n minus 1, and then if it's S, okay, then Q flag is set. If it is S, Q is given 1, okay, and the minimum value is actually sent to the destination, right? And whatever is in the operand, right, that is if, okay, yeah, in this condition, whatever is the minimum value that is being sent to the register. Now it is going to check for minimum. Okay, if it is no, then it should, is it maximum? So the maximum value is also checked, right, for signed and unsigned values. This is for signed saturation and unsigned saturation. So you should know the minimum limit, and which is the lower limit and the upper limit of both signed and unsigned. So which means 4 values you should know, right? So what are those 4 values? You can see this from this tabulation also, right? Let me just show you. Yeah. So this value you take, okay, so this value is here, okay, and for unsigned, okay, it starts with 0, this value is here. Similarly, you have the other values which are 2 raised to n minus 1 minus 1, so that is brought down here, okay, and 2 raised to n minus 1, this is also brought down here. Okay, so 4 values. You need to know the lower cutoff and the upper cutoff values of both saturation and signed saturation and unsigned saturation. So suppose, okay, so minimum, fine, the value is smooth. Now let's go to the other case when it's maximum. Okay, when it's maximum, is it S? Okay, if it's S, then 1 is smooth, and the maximum value is being sent to destination. What is the maximum value of these values? So if you use an unsigned, then this value is going to be sent. If it is signed, then this value is going to be sent to the register. Okay, So if it is none of them, okay, if it is none of them, not minimum, not then what is going to happen? Whatever is the operand, the same value is going to be sent to the register. So we will see this. Okay, we will see how it actually works. Fine. Now, there's a small example that is taken up where, we are trying to increase the intensity. Now, I think all of you are very much aware of this RGB values, right? Red, blue, green. So using these three colors, we can actually create or represent any other color, or probably, upscale the colors. So generally, you can take this as an example. When, try connecting your laptop to your, say, high definition television, right? You can see that there's a huge change in the color saturation, right? So here it might look, faded blue. Okay, this flow chart, for example, it might look faded blue, but then there in your television, it might look a little more rich. So how is that possible? We are going to upscale the values, right? So upscaling values are also done with the help of this saturation programs. Okay? So one example of such is taken. Okay. Yeah. So this is the example. R1 has some values, R2 has some values, both are being added. Okay, and then it is going to check, and that value is going to be set. So both are seen. Okay, so 100 and 135, it's 235, it's less than or equal to, fine. So 235 is sent. Now in this case, it is 221 and 100. So it is actually greater than 255, right? So what is going to happen? This value is not going to come and sit here, but then the greater value, which was 255, is going to come in, because that's the limit that I have set, right? I cannot go beyond the upper limit. Okay. Now let us take this as an example. 97 and 100. So it's 197. It is less than or equal to this value, so it will come and sit. Right. So what are we trying to do here? We are trying to add R2 and R1, and the values of this is going to sit in R0. So R1 and R2 is added. Okay, and it is going to come and sit in R0. Right. So this is used to simultaneously increase the brightness of RGB components of a digital image without overflow. So what is overflow? Remember the V flag that I was talking to you about, N, C, V, Z, Q, right? So now this overflow is referring to V flag. So whenever there is an overflow here, right? So here we can see that, it is exceeding. So without, going beyond the value that is being set, the value set here is 255. It doesn't go beyond this. So 325, 321 is not taken. Then the maximum limit is actually taken in Q flags. So that's why it says UQ, unsigned Q flag. Okay, adding these numbers, which is, are not is the destination, R1, R2 are the register. So I hope you have understood this, right? Any doubts up till this point, students? Is it all clear? What are we trying to do with these programs? Yes, can I proceed? Okay. So, these are, some of the instruction sets and, the formats and what it actually does and how many operands are involved. So when I say add 8, okay, which means, it actually is having 4 cross 8. So which means 4, 4, 4, 4. So the 32 bits is actually divided in that format. Okay, so 8 bits are taken in 4 groups. So that is 4 into 8. Okay, so when we do this Q add, okay, so it is actually referring to the 32 bit. Okay, so when I just use Q add 8, okay, then it's referring to 2 raised to 7. Okay, 2 raised to 7 minus 1, so that becomes n. N is equal to 8. Okay, now n is here 16, so 2 raised to n minus 1. Okay, so 2 raised to n minus 1 minus 1. So n minus 1 here is 15 minus 1. Right? So the same workout that we saw previously. Similarly, this is for add and then subtract and similarly add. So what are we trying to do here? We are trying to have the source and the destination registers. Okay, Rn plus Rn, Rn minus Rn. Okay, so Rn is this. Okay, and that is operand 1 and operand 2. Okay, so if I have to tell this in operand form, then it's going to be operand 1 minus operand 2. Okay, so yeah, so Rd is here, Rn minus Rn. So yeah, you can just go through this, right? So it is pretty simple as explained. So each instruction works on a 32-bit value or two 16-bit values or 4 groups of 8-bit values all at once. The Q flag is set when saturation occurs and no other flags are affected. So whenever there is a saturation, which means it has met its limit, then Q flag is set. If not, then Q flag remains as it is. Okay, so you can probably take this as an example, right? And then you try to add, and then you get a value, and then if it's going beyond the set limit, okay, then Q flag is set. If not, then it is reset. Yes. Fine. So that's the meaning of this 8. So 1, 2, 3, 4 groups of 8 bits, right? So 4 8s 32. That's how it's going to go. Okay, so what is this Q flag all about, right? So Q flag is nothing but it is the bit 27 in APSR. So the program status register, right? So in this, it's the 27th bit. Okay, so Q flag is a dual purpose flag. So we can use it when we add, subtract, okay, and we can use it for showing overflow, and we can also use it for saturation. As I mentioned previously, this Q flag can be configured for 2 purposes, or it can be called in for 2 purposes: to check if there is an overflow or to check if there is a saturation. Okay, so basically Q is referring to saturation primarily, but it can also perform the function of checking the overflow function. So you can take this as an example, right? So probably you can you have a bike, say for example, which can go up to 60 kilometers per hour, right? And you can also use it for going at 30 kilometers per hour. So it's a multi-purpose. You can either go slow or you can go fast, right? So this Q flag here is going to check with the overflow format, or it is also going to check with the saturation. What is the saturation? The limits are going to be checked. If it is less than the lower limit, then the lower limit is going to be taken. If it is greater than the upper limit, then the upper limit is going to be taken. If it is between both of the limits, like how we saw here, right? If it is between both of the limits, then what is going to happen? Whatever was the operand, the same thing is going to be transferred to the destination register. So I hope this flowchart and the explanation thus far is clear. Students, any doubts till this point? Yes, can I proceed? Okay. Now, this Q flag is a sticky flag. How is it a sticky flag? So we can either clear it or we can transfer it. So 2 functions again here. SIMD and saturation instructions. This is for multiply, add, subtract, instructions. Can set Q to 1 but not clear it. Okay, so it can either make it 1. So only way to make Q 0 is to use these 2 instructions, MRS and MSR. Okay, so I will show you what these instructions are, which is MRS and MSR. We'll be able to understand. So which means there is no way to clear Q. So we do not have control on Q. But then I can set Q to 1, but then I cannot make it 0. So the only way that I can make it 0 is using these two instructions, MRS and MSR. Okay. There is no condition code or conditional branch that tests the Q flag, just like branch if equal, branch if not equal, right? So compare. So we do a subtraction there in compare, right? So to check this condition, there is no specific branching instruction to check which condition Q, the status of Q, right? We do not have any special instruction, right? But then what we can do is we can just transfer the value from the register to the status flag, right? Or from the status flag, from the flags to the register. So how do we do that, right? So we use the format called MSR, okay, N, that is negative, 0, carry, overflow, Q, right? So values of register is moved to the flags. Okay, so this is the format. So what is happening here? So Rn is nothing but the bits which is from 27 to 31, Rn. Okay, Rn. So these bits are transferred. Okay, the values of these register is transferred to the status flags, right? So 31, so 27, 28, 29, 30, 31. So there are 5 bits, right? So 1, 2, 3, 4, 5. So these 5 bits will come and sit in these 5 flags: negative, 0, carry, overflow, and Q, which is saturation. Now, what happens to the remaining? Which is from 0 to 26th bit, okay, are actually unaffected. So the thing that happens here is from 27 to 31 only is transferred. The rest of the thing will remain the same. Now, if we reverse this, right, from APSR to RT, okay, so what happens to the destination register? What happens now here? Okay, whatever is the values of these program status registers, which is N, Z, C, V, Q, that can be transferred, and these bits are altered. Okay, bits from 27 to 31, which is 5 bits, are altered, and the remaining bits are filled with 0. So whenever you're transferring from flags to the register, okay, zeros are filled with bits 0 to 26. But then when you're transferring from register to flag, only these 5 bits are affected, and 0 to 26 are unaffected. So which means here flags have a higher priority. Okay, so whatever is the value of flag, that is being written to the register, but from the register you're only manipulating 5 bits of the flag. Okay, 5 bits are only taken. Okay, so how do we test this Q flag, right? So now, as I told, there are two formats here, MSR and MRS, right? So MRS, so let us take this. So this actually copies, okay, the flag values to R0. So what are these flag values? As I told you, 5 bits, right? N, Z, C, V, Q. So these are only transferred, and the remaining bits are not changed at all. And if I have to check the value of Q, then what I'm going to do, I'm going to take the 27th bit. Remember, I told you this is 27th bit, right? So 27th bit, it is checked with 1 and with the R0 value. Okay, R0. So this is how we use the test instruction. So how do we actually check the Q flag? Next, branch if not equal. Okay, so if Q flag is set, okay, branch if not equal if Q flag is set. So in this way, this is the only way that I can check the Q flag, by using this APSR. Okay, moving the values of flags to R0 and then using test, right? So once I use the test, which means it's going to compare with 1, right? And if it's equal, okay, branch if not equal, then the flag is set. Okay, so branch if Q is equal to 1. So I don't have option to clear, as I told you. So the only way that I can clear is using MRS. Now let us see what is this MRS here, and I'm going to use a special instruction called BIC, right? Bit instruction clear. So the values or the contents of these flags are moved to R0, and remember, um, uh, this is actually moved from 27 to 31st bit, right? And the rest all values are filled with zeros. So BIC. So what I'm going to do, I'm going to have from this 1 to 27, right? And I'm going to use R0. So R0, I've already moved the value from the flags. So with R0, so bit by bit, I'm going to clear it. Okay. So in this way, the 27th bit, which is the Q flag, is also cleared, which means I am making it 0. Okay. So ultimately using MSR, okay, the first one that we saw, the value or the contents of R0 is moved to flags. So I am not directly changing the Q value to 0, but then I am first moving the making the value 0 here in the register, and those values I am moving to flag. So that's the only way that I can clear the flag. So these two instructions are special, MSR and MRS. Okay, fine. So these are some of the limits that I told you about, right? For signed saturation, unsigned saturation, what is the minimum value, what is the maximum value, right? So these are just repeated here, and then yeah, we have seen this as well, right? And what else we have seen? Yeah, Q add 16, okay, 32, then for unsigned, and yeah, addition, subtraction. So here what is happening in non-saturating addition and subtraction, this affects the G flags for use with or without select instruction. So we will see that, right? We will see that. And in this way, we can even use signed multiplication, okay, unsigned, okay, signed multiplication, okay. So yeah, so we will see all this format. So as of now, you have to remember the most important thing are these limits, okay, and remember the flow chart which I told you, okay, the minimum value, the maximum value. So if it's between, then okay. So we have seen it up till this point. Just like I was mentioning about this flow chart, remember. So if it is minimum, then the limits is set. If it's maximum, then the maximum limit is actually given. If it falls in between, then it's a good number. There's no problem in having the limits. So just the same number is sent to the register. Fine. So I think up till this point, we are clear, and how much of data, 8, 16, 8, what are all those referring to? Also we are clear. Okay. So we are going to see 32-bit program 1. Okay, we're going to see 32-bit saturated, okay, to 16-bit number, okay, and signed operation, okay, 16-bit, how it's going to change from one form to another form, okay. And in R3, okay, in R3 we are going to see these values, right, the upper limit and the lower limit. And R4, when Q is set to 1, then what is going to happen? So we will actually see this in the operation. Okay, so let me just share that to you all. Yeah. So first we'll start off with signed numbers. Okay. So a location, okay, a value, a number is actually given to R1. Okay, so beyond which it's not going to happen, which means the transfer is not going to happen, but the limits are itself taken. As I was mentioning, right, the number is beyond lower limit. So we are just going to give the value, and we are going to check with the limits, the upper limit and the lower limit, and we are going to transfer accordingly. So R1 here, okay, so we are going to use we're going to compare this, okay, with the 16 bits, and the value or the final value is actually transferred to R2. So we are looking at signed saturation. So when I say signed saturation, so you must think of the limits of signed values, the upper limit and the lower limit. Okay, so yeah, then here the flags are actually moved to R0. Okay, so which means 27 to 31. Okay, those values are actually moved, and rest of the things, as I told you, are going to be loaded with zeros. Now here BIC, okay, so this is used to clear, okay, clear the flags, and you can see that Q is actually going to be made 0. I will show that in debug when we get into debug format. And here we are going to copy the value of whatever is in R0 to the status registers, so which means 5 bits of R0 is going to be taken: 27, 28, 29, 30, 31. So these bit values are transferred, and rest of the bits, okay, which is 0 to 26, is not affected at all. Okay, and again, now we will take another number, and then we'll try to do the same operation, right? So you can see that all these are same: 1, 2, 3, 4, right? 1, 2, 3, 4. So same operations are performed, right? So we are taking a lower value, we're taking a higher value, and then we're going to check what is going to happen, right? And then we will probably take something within the limits. Okay, so one we are going to take beyond the lower limit, okay, which means extreme negative value, and one we are going to take beyond the upper limit, so which means extremely higher positive value, and one we are going to take within the limit, so which lies between the limits of upper and lower. Okay, and we will see if the same value is transferred or not. So same thing, comparison. Okay, moving the value to R0 and comparing it with the values here. Okay, and R0 is moved to the flags, and then it stops branching. Okay, so we will see how this is executed. Let me just save it, translate, 0 errors, which is good. We'll get into build. Okay, 0, that's fine. Get into debug. Right. So here the important thing is we are going to look at this Q flag here. Okay. I hope you're able to see that. Right. This Q flag is what we're going to check. Okay. Right. So let us start with the execution. Right. I'm just giving a number. So that number comes and sits here in R1. I'm doing the stepwise execution. I'm using F11. Right. And after that, it's going to check the limit. And if in case it is beyond the limit, then the negative value is actually transferred, right? So we have seen that FFFF8000. So this is the limit. So that has been transferred to R2, right? It compares, checks if the value is too negative. It will not take that too negative because it's beyond the limit, takes the negative limit and puts it in R2. Okay, now we are going to check. See, you can see that Q flag is actually set because it was beyond the limit. Okay, and Q flag is checked, so which means it has reached its saturation level. Okay, then next again I go with clearing of Q flag. So how do I do that? Okay, so it is actually doing an ANDing operation, right? ANDing operation between R0 and this values here. So you can see Q is 1, and then it will consequently become 0. Okay, so Here now, R0's value will be moved to these status registers, which is N, Z, C, V, Q. So N is already 0, Z is 0, C is 0, V is 0, Q should now become 0. Okay, because what do we have in R0? In R0 we have 0. So it is like transferring zeros to the flags. Okay, so now when I go with the next step, immediately this Q should turn 0, right? So it has turned 0. So the values have actually changed. So next, I'm going to take another set of number into R1. Okay, now this is beyond the upper limit. Now, since it's beyond upper limit, so we have, the value there 2 raised to n minus 1 minus 1, right? So we take that value, right? So which is 0.00007 FFF. So this is the positive value. And again here Q has become 1. Why Q has become 1? Because it has reached this upper positive value. Okay. Now I want to clear this off. I don't have a specific instruction to clear it, but instead what I will do, R0 is already clear. So I will just move that to the flag. So how do I do that? Okay. I take the values, okay, and I do a ANDing operation. Okay, so with that ANDing operation, what is going to happen? My R0, you can see R0 has become 0. Okay, and that 0 I will be actually now transferring to the status register. So which means Q also should be become 0 now. Yeah, so Q has turned 0. So next I send another number which is in limit, not to negative, not to positive, but in the medium range, and the same value should be actually seen in R4. Okay, that's the whole idea. So R1 I have the value here, right? 1 2 3 4, and it's going to check. Okay, sign the saturation, it's going to check. It's all fine. So you can see that the same value has actually moved to R4. So unlike the previous time, you don't find moving to the negative value, nor you don't find moving the positive value, right? So R2 is actually referring to the negative limit, and R3 is referring to the positive limit. And here R4 has the value which is in between the positive and negative limit. So the same value is transferred, and we can see that in R4. And Q is 0 here because it has not reached any saturation. It does not reach the upper limit, nor it has reached the lower limit. So Q will not change. Okay. So in that way, you can actually understand how these programs are executed. So any doubts here in the signed operation? Is it all clear? Can we proceed to the next one? Okay. So now we will go to the unsigned operation. Now limits are going to change. Okay, so just that the program would remain the same. Right? So you can see here the programs would remain the same, but then instead of SSAT, it is USAT. See, SSAT becomes USAT. Okay. So similarly, we're going to compare, and we're going to move the PSR values to R0, and then I'm going to do an ANDing operation. Okay, and it's going to clear the bits, and those cleared bits are moved to the status flags. So let us just execute this. Zero errors, which is good. Translate and build is fine. Get into debug. Yeah, get into single step. Fine. So the value of this R1 has to come and sit here. Okay, then it's going to compare beyond the limit. Then what is going to happen? Q is going to be set. Okay, so since Q is set, okay, what is going to happen? We're going to see, we're going to do a bit you know, bit clearing. Okay, so now R0 is 0, so that value should come and sit here. Q should be made 0, right? Then we move a different value, just 3003, and then 0000. And then since it's beyond the limit, okay, we are going to move that value, right? Positive limit. Okay, so this is the positive limit. 000 FFF is actually returned to R3, right? So because the number is beyond upper limit, okay, this number is beyond upper limit. Same examples we have taken, right? Just that, you know, we are going to change the signed and unsigned values. So the limits are going to change, right? Lower limit is 0 and upper limit is 000 FFF. So 0 to F, right? Okay. And the next one is, you know, we're again going to go for clearing this Q value, because the main reason here is that, you know, we are checking the value of Q. We're checking if it is going above the negative value, okay, or beyond positive value, and we're going to check if it's in between them, right? If it's between them, then we're going to transfer the same number. Okay, so it's made 0, and once it's made 0, right, the next is to make Q 0, right? Q is made 0, and then I take one number between the limits 1 2 3 4, and then I shift it, right? Then I use you know, the instruction where I can just transfer R1 to R4. Okay, so you can see that the lower, the 16 bit, okay, is actually transferred to R4. Okay, so R4 is transferred. Q remains 0 because it has not reached its upper limit or lower limit. Okay, so in this way, you know, we can also check out for the unsigned numbers. So the limits are going to change. We're going to play around with the Q values. Okay, we're going to extract the value of Q. We're going to send, you know, reset a register and send that to the status flag so that we can reset the values, right? Okay. So the next, you know, that we will be looking into is the floating point numbers. So I think all of you have studied these floating point numbers, right? Have you all studied floating point numbers? Yes, no? Yes? Have you all studied? Okay. So there are some important things that you know, we need to look into. Yeah, thank you for the response. So let me, before I come to this, you know, this section, okay, let me just go to the previous ones and explain you, you know. So this is the exponent part, and is the fractional part, right? So we have the exponent part, and then we have the fractional part. So you add them up. So it should be giving you, you know, the values, 31-bit values, and then here, you know, we get to know if it's a positive or a negative number using the MSB bit. So we have, you know, seen this exclusively in test instructions, isn't it? So checking the value of MSB, 0 if positive, 1 if negative, right? And excess, so how, you know, it changes. Fine. Yeah, how floating point numbers, right? So now what we will do is just check this format here. Okay, I have some number here starting from 0000, and then it moves on to 111101. Okay, just as a random number here. Okay, so which is F, and then just go through the slide, students. Okay, so as you can see here, we have some value, uh, you know and the how the exponent part is taken, and yeah, so how it's represented as plus. So plus is 0 here, and then 136. So n becomes my 136 2 raised to n, right, minus 127. So this is fine with all of us, right? So the integer processor and floating point, remember I was telling you about 8085, 8086 and 8087. So that is one such example. So for integer processor, we use registers R0 to R12, right? And those are also called APSR flags. And registers from S0 to S31 is utilized by floating point registers. So why do I need this? These both act hand to hand, and they will be able to execute things together, right? So which means these registers are not to R12, right, will be exclusively used by for the operations of integer, and these will be exclusively used for floating points. So together they combine, and they get connected to the main memory, and I have the integer part, and I have the decimal, which is the floating point data. So I combine them together and I get the full number, right? So for that we have some instructions here, right? So we will be seeing them exclusively. Yeah, so these also are the set of registers for floating point. As you all can see, S0 to S15 may be modified by functions, and S16 to 31 may be preserved by some function. So generally we will be using S0 to S15, right? And D0 to D15 may be used to hold 64-bit values, right? Okay. Next, we'll be seeing a few instructions here. Okay, how these values are loaded. So as I was mentioning, I think these constants, you are very much aware. Let me move on to the main instruction part, which we are actually using for our program today. Okay, so let me just show you that. Yeah, this is also one more important thing that you guys need to look into. Let's say I am giving a syntax of v move, okay, sd comma sm. Okay, so what is going to happen? Whatever is the value, the floating point register, okay, whatever is the values here, okay, that is moved to sd. Okay, and yeah, so the same thing here for this. So now when I have two floating point registers, okay, from two floating point registers, I'm moving to the integer processors, which means the regular registers that we are using. Okay, so SM will be moved to RT, and SM1 will be moved to RT2. So it's just like this. Let me show you. Okay, so SM comes here. Okay, and SM1 gets in here. Okay, so there's a kind of balance between them, how data is moved between floating point and the normal registers, right? Okay, so if we have to move value from core registers to floating point, core registers are the regular general purpose registers that we were using so far. So RT again here, let me just clear this. Yeah, so RT is moved to SM, and RT2 is moved to SM1. Okay, fine. So this is also one important concept. Please make note of this. Okay. The next one is very interesting one, where we will actually be converting, okay, from unsigned to floating point. Okay, now let us take the first one. Okay, so from integer, okay, unsigned integer, we are actually converting to floating point. So that is what it is referring to when I say U32. Okay, so it becomes unsigned integer value, and that is being converted to floating point. So here, now you know the meaning of this SD comma SM, isn't it? So we are using floating point registers, okay, and SM is an unsigned integer, right? So unsigned is referring to SM, and the floating point will be referred by SD. Now convert, okay, convert from signed, okay, to floating point. We saw unsigned, so here now signed integer. Okay, so convert 2's complement integer to a floating point number. So this will actually convert, okay, the integer to floating point. So I hope all of you have looked into this in detail in your theory, right? So I'm just brushing up the syntaxes here and the operation. Okay, so similarly now 32, when I use F32 and U32, then it's a floating point number. F is referring to float and U is referring to unsigned. Okay, yeah. And then similarly, from floating point to the signed type. Right? So we will see them how it actually works. So F is actually single precision, and dot S32 is 32-bit signed 2's complement integer. I will show you this, right, as 32. We will see this, and we will also see the negation part as well. Okay. Right. The other important thing that I wanted to brush up is regarding the instructions. Yeah, this one. So here when I say we add F32, right? So I have a destination register here. So this S, as I told you, is associated with floating point registers, right? So N and M are added, and that value, final value, will come and sit in D. Okay. Similarly, subtract and negate. Okay, so which means minus SM. So whatever value, say 10 and minus 10 is moved to SD. So I will show this also to you. Okay, so meanwhile, the absolute value. Okay, so the sign bit is cleared. Now what is referring to the sign bit? The 31st bit, 0 to 31st, so the last MSB bit. So that is referring to the sign bit, so that is cleared. Okay, and multiplication, so N into M is done. So whatever the value will come and sit in D, right? So division, square root, MLA, okay, which is floating point, multiply and add. So two operations are happening here, special instruction. Two operations, multiply and add, where first N and M, okay, are multiplied, okay, and whatever is in the destination, that is added, and the final destination is updated. Okay, so multiplication happens only between these two, which is N and M, and addition happens to the product of N and M and SD. The final value will be updated in SD. Okay. So similarly, for like addition, we have subtraction also. Multiplication remains the same, but subtracted with SD value, and SD's final value is changed. Okay, so yeah. Similarly, we have comparing two registers, SD, and just like how we had compare C MP, right? So here also we have comparing values SD and SM. So which means whenever we use a compare operation, then subtraction is happening, right? SD minus SM, subtraction happens, and it updates the flags in the FPSCR. I will show you these flags as well. Okay. Next, the floating point compare register to 0, right? So we are going to see if the destination is actually, minus. So whenever compare is there, we are going to minus SD minus 0, and it updates the FP. Okay. So similarly, the moving the values to N, Z, C, V, right? Here also it's possible from floating point to, the CPU flags. So CPU flags are nothing but the one that is dealing with the integer part, right? So those regular registers and the status registers of those. So that is nothing but your APSR, and FPSR is nothing but the floating point status registers. Okay. So this is the important thing that we need to look into. Now, let us get into the program, and we will see how it executes. Okay. Okay, so now we'll get into the execution of floating point. Okay, so as usual, we have the declarations done, and then we are loading R0 with a value. Okay, and so whatever is the contents of this R0, so this is a register, so these contents are moved to R1. Now we need to actually activate the floating point operation. So what we do is we shift it, okay, and we do an ORing operation. Okay, so I think all of you know how this OR operation happens, right? So it happens bitwise. So each bit is taken bit by bit, and then the ORing operation happens. So the result is actually stored in R1. Okay, and whatever is in R1, now I'm going to move to the location which is pointed by R0. R0's location is pointed here, right? So that value will be shifted. Now I'll be loading a value to R1. Okay, and these are all my floating point instructions, as you know, right? So we move, we convert, we move, okay, add, multiply, subtract, negate, okay, the absolute value, division, multiply, and add, right? So these are with different registers in the floating point unit. Okay, so I think all of you are now very much aware with this concept. So let us try and execute them, and we'll see how it goes. Yeah, 0 errors. Let me build it. Okay, which is 0. That's also good. Let's get into debug mode. Say okay for that. Now here, remember we were looking at these PSRs here, right? PSR in signed and unsigned, where we were dealing only with Q. But here for floating point, now we are not going to see here, but then we are going to scroll down and we're going to see exclusively FPU, floating point unit, right? And here we're going to have the set of registers, right? S0 till S31. So all these registers are what we are actually going to look into, right? Fine. So we start. Initially, we're going to deal with the core registers, right? So in R0, the value is going to be moved, right? So this value is moved to R0, and whatever is in R1, okay, that is moved to R0, right? So R1 is 0, you can see here, and I have given the address here, right? E000 ED88. So I have given the address here in the memory, and you can find that these zeros have come here, which is in red. Initially it was not there, and these zeros are moved right now. So that's why you can see the color difference between this black and red. Okay, so now next we're going to store the value, okay, from R0 to R1. So R0 to R1, the values are stored, and as I was mentioning, now we're going to activate the floating point registers, right? And we are going to deal exclusively with these. So how we're going to convert, okay, this, or we're going to move this value to S7, right? So this value is moved here to S7, okay? And similarly, we are trying to do a conversion between unsigned value to floating point between S17 and S17, right? So yeah. And to S8 we will just move one value, right? So this value is moved here to S8, to S9, another value. Now we're going to add them both, okay? So manually you can do this, right? You can actually add them, and the value is going to sit in S10, right? So here you can see that this is the floating point, and it is just moving the value, moving the immediate value to S9, moving this floating point value to S8. Both are added, and the final value is being seen in S10. So the next one is, in S11, you can see that it is a multiplication of both S8 and S7. So whatever values is in S8 and S7, right? So multiplied and value is being seen in S11. So similarly, you can subtract them. Okay, let us check this negate. So whatever is in S12, right? So S13 should have minus and the value of S12, right? So you can see here, right? So you can, the negated value, right? The negative, you can change all the ones and zeros. The minus, okay, you can make it minus, and the absolute value is taken of 13 and it is moved to 14, right? You can see that we will come back to this PSR once we of course we do not have that instruction here, right? It's all about only multiplication and division. Okay, so we will be sticking with these registers here. Yeah. So next is multiply and add, as I explained, right? So multiplication will be done with S8 and S9, and then that value will be added in S11, and S11's value will be updated. So here this value should change here. S11, see, it is updated. Right? So you can actually cross check with these values, okay, and you can see if these are working fine or not. So ultimately, we are looking at accessing the floating point unit here, right? You have to scroll down. We were first using these core values, okay, core register values. Then scroll down. We are using now FPU, floating point. So these are differentiated. How these instructions look, like vmove, okay, vadd, vmul, okay, vmla. So all this, right? So you can try doing a manual calculation and just cross check if you're getting the same values in these uh, banks of registers, right? So I hope all of you have understood this concept, right? Any doubts here, students? Okay, fine. Thank you.